All right, welcome back. So we're still talking about the cohomology of Eilenberg-MacLane spaces. I guess this is part 4. This is all taking longer to say than I anticipated, but that's okay. So in the last video, we looked at a theorem of Borel that told us if we had a simple system of transgressive generators in the fiber, that told us about the cohomology of the base. In particular, it was just going to be polynomial on the transgression applied to those generators. And so we looked at how that played out for kz mod 2, comma 2 a little bit, but we still don't have a precise description. So we'll finally get that here. But first, let me remind you about some notation and some terminology. So remember that our square capital I is really a sequence. So that's like square I1 after square I2 after a bunch of things and then square IR. And we said that this sequence I is admissible if each ij is greater than or equal to 2 times the next term, so ij plus 1. And I think I had a typo. I looked back and it looked like there's a typo in my notes where I said that this was strictly greater than. This should be greater than or equal. And the reason is that I think of these as not addendable. That's how I remember admissible. And remember, we have an addend relation where we can change square A square B into a bunch of other stuff using our long addend relation. There's some binomial coefficient, sum of a bunch of terms, and that happens precisely when A is less than 2B. So I want this to say that the addend relation wouldn't hold on any successive pairs. Okay, and then if I is admissible, we say it has excess, and we write E of I, and this is sort of how far away from addendable it is. So I said this out loud, but let's get that in notes. This only is defined if our sequence is already admissible. And there are a couple ways to calculate this. So we said you can take 2 times the first spot minus the degree of I, so that's just the sum of all the terms. And if I write that out, then I'll have a minus I1, so the 2I1 cancels, I've got just a single I1, and then I subtract off I2, and so on up to IR. Or I think we wrote before that this is I1 minus 2I2 plus I2 minus 2I3 plus and so on, and then the last one sort of ends up stuck on its own. There's no minus 2IR plus 1 since our sequence terminated. But this last version really tells you that yes, we are measuring how far away from addendable this thing is. Okay, so at long last, with all of this notation and terminology, we can say precisely what the cohomology of our Eilenberg-MacLane spaces is for these kz mod 2 ends. And this is a theorem due to Serre. So the cohomology of kz mod 2n in mod 2 coefficients. Serre proves that this is polynomial in square I applied to iota n. Make sure that's readable. And this is where I is particularly nice. So let me make that precise. This I runs over all admissible sequences. With the restriction that we don't want too much excess. So the excess of I has to be less than n. Okay, so that I think is kind of feels like a strange requirement at first, so let's look at some baby examples just to get a feel for it. So for example, when n is 1, what does that say? Well, this is really just a sanity check. The excess of I has to be less than 1, so it's 0. So we're only looking at square 0, right? Because we take the first thing in the sequence and subtract off all the other things. The only way we're going to get 0 is if they're the same. And we want these to be admissible sequences. So square one is not interesting, though it happens to be 0 anyway. Okay, so only square 0. And remember that our cohomology of k z mod 2, comma 1, that's just our p infinity. So in mod 2 coefficients, we get z mod 2 on this fundamental class, iota 1, so just polynomial generated in that single class. And yes, that is just square 0 applied to this thing and then take polynomials. Okay, so that's just a quick sanity check. What does this say if n is 2? Well, then our excess can only be 0 or 1. Okay, 0 again is still not very interesting because the only option there is square 0. But now we're allowed to have square 1. Remember, excess is really about sort of how the successive terms relate, so it's not just square 0 and square 1. There's also square 2 square 1, for example. Okay, so notice, not a demable, right? Because 2 is not less than 2. And the excess is how far away we are from that addendable. And here this is like the edge case. So our excess is 0. And in fact, if we take, our excess is 1. Yes, our excess is 1. The only thing with excess 0, square 0, as I said. Okay, so our excess is 1 if we take the 2 minus the 1, then we get 1. Okay, great. Okay, I don't know what I was trying to say there. Then, for example, square 4, square 2, square 1 also has excess 1. So again, this is like that sort of edge case where we're really as close as we can be to being addendable without sort of extra stuff, without excess. But we say that's excess 1, okay? And again, I would take 4 minus 2 minus 1. Yeah, that's going to give me 1. Okay, so that does have excess 1. And so on. And so there are lots of things like this. And in fact, they'll all look like the sequence of powers of 2s going backwards. Notice that something like square 3 square 1 has excess 3 minus 1, so that's 2. And so that's not something that we'll see. Okay, so the claim here is that the cohomology of kz mod 2, which we were looking at in the last video, in mod 2 coefficients. I've been working in mod 2 coefficients this whole time, but ultimately I want to say something about other coefficients too, so I keep emphasizing it. Well, the claim is that this should be polynomial in these admissible squares on iota 2 where the excess is less than 1, so these sorts of sequences. So yeah, I've got iota 2, that's square 0 on it. I've got square 1 iota 2, I've got square 2 square 1 iota 2, and I'm running out of space, but I've got square 4 square 2 square 1 on iota 2, and so on. And of course you can see as these sequences get longer, it gets more annoying to write the squas every time, so we could just say squa 4 2 1 on iota 2, so on. Okay, remember that we did start to see some of this stuff in the last video, right? We saw iota 2, we saw square 1 iota 2, we saw the product of those things. I think we even saw this next term, square 2, square 1 iota 2, though we didn't get into polynomial sort of combinations in higher degrees, really for lack of space and time, I suppose. But okay, continuing on, what does this say for n equals 3? Of course, I know you could work this out for yourself, but I think it's kind of helpful to see sort of how this pattern's going to go. So of course, we still got square 0. We've still got all the stuff from xs1, so square 1, square 2, square 1, square 4, square 2, square 1, and so on. But we've also got things with xs2. So for example, square 3, square 1. And now it can be a little confusing because remember, we can write square 3 as square 1, square 2, but if we want it to be an admissible sequence, then we don't, right? Square 1, square 2 is addendable, and the addend relation tells you it's square 3, okay? But square 3 is sort of not addendable on that side. It's only by accident that it ends up on the right hand side of the idem relation. Okay, so square 3, square 1, we've got 3 minus 1. Yep, that had excess 2. We saw that last time. We get things like square 4, square 2. It doesn't have to end in square 1, for example. Okay, so 4 minus 2 is 2, and so on. Okay, I'm not going to keep writing these out. I just wanted to point out that sort of you do get some more interesting combinations, but they're still always going to look like these decreasing sequences because we've got that admissible condition. Okay, so maybe it's worth pointing out at this point, whoops, sorry, jumping around a little here, but maybe it's worth pointing out that really we see more and more of the Steenrod algebra as we go. So as n gets larger. Though we're seeing only sort of squares written in nice particular orders. Okay, so in order to prove this, we're going to need this lemma, or we're going to use this lemma, which has 2 parts. So the first is that if I is admissible, with the excess of I being greater than n, then already we should know that square I on iota n is 0. Okay, so that's why we're not including things with excess greater than n. But we're also not including things with excess equal to n, and why is that? Well, if I, again, is admissible, and now with excess equal to n, the whole point is that we can rewrite it as something else. So we look at square I on iota n, and what we should do is recognize that really this is square j on iota n raised to a power 2 to the k. So this looks like a polynomial in something else. Maybe let me write that down. Where what's going to happen with this j? Well, we'll want j to be admissible so that it shows up in our list, and j will have excess less than n. Okay, so again, the first part is saying, oh yeah, we don't need stuff with excess greater than n. And the second part is saying, well, sure, you can have stuff with excess equal to n. It's just that you could rewrite that as polynomial stuff, and so you don't really need to account for that. And in fact, if you had that stuff in there, then you'd have extra, right? Okay, so let's prove this lemma. Maybe let me at least start to prove part 1 before it goes off the screen. Okay, so let's assume the excess of I is greater than n. Of course, I'm assuming it's admissible. It doesn't even make sense to talk about excess unless it's admissible. And what is the excess? Well, I guess our middle version of this was we could take the first term minus all the other terms. Okay, and so I'm saying that's greater than n. What does that tell me? Well, I could rearrange and say that tells me that I1 is greater than n plus I2 plus ... up to IR. But this is equal to the degree of, if I apply square 2 after square 3 after so on, square IR to iota n. Iota n is a class in degree n, and then square IR takes it up degree IR, and so I add up all of these degrees, and that's exactly what I've written here. And so square I1 on this thing is, well, I1 is going to be greater than the degree of this cohomology class, right? So remember, these are, the cohomology of a space in Montague coefficients is an unstable module over the Steenrod algebra, meaning that those high degree squares kill lower degree things. And so square I1 is going to kill this element because this degree is lower than I1. Okay, so that tells us that, yep, this whole square I is going to kill it. Maybe you get something interesting up until you've applied square I2 after all this other stuff, but then you apply square I1 and you're done. So the thing has died. Okay, then for the next part, we don't want to show that what we get is 0. We want to show that if you have excess n, then we can rewrite that term. So let's go ahead and do that. Okay, so suppose the excess of I is n. So now I'm going to do almost exactly the same thing. I take I1 minus I2 minus up to IR, and that's equal to n. And that's going to tell me that I1 is equal to the sum of these things. You probably didn't need me to write that out again, but I like having things match. Okay, and now I want to consider essentially the same thing. So I look at square I1 applied to square I2 after all the others, after square IR applied to iota n. And I notice that now the degree that this thing is in is precisely I1. But remember, one of our rules of the Steenrod squares is that it extends the cup square. So if we're in the correct degree, and we are, then we should just get that class squared. So this is square I2 after a bunch of stuff, square IR applied to iota n, and then squared. Excuse me. Okay, so now we look at the excess of this sequence that we're left with. Oops, I want to start at I2 and go to IR. And getting everything backwards. Okay, the point is this excess is less than or equal to n, right? We just peeled off our first term. And now when we compute the excess, maybe that's sort of less obvious from this formula we were just working with, but remember the one that looked like I1 minus 2I2 plus I2 minus 2I3. So we sort of compute these things with successive pairs, and we just remove the first pair. So this thing could only have gotten smaller. And if this is less than n, so that we have excess less than n, then we're done. We've done it, right? We can take that as our j. It'll just be I2 through IR, and we've made this thing some power of 2 times that. Okay, if not, then we repeat the process, and we'll pick up another power of 2, and so on and so forth. Okay, so that ends the proof. Okay, so again, just kind of doing some sanity checks, making sure that we understand what this is saying, because it's easy to get lost in the notation. If n is 3, we're saying that, or really Sayre has said that the cohomology of kz mod 2 comma 3 and mod 2 coefficients should be polynomial on square i's applied to iota 3, where the excess is less than 3. And so square 3 iota 3, well, that's just a 3 minus 0, if you like. The excess here equals 3, so this is not needed. But we're at degree 3, right? And so the point of what we were just checking is that indeed this is iota 3 squared. Oh yeah, of course, we're squaring the thing in degree 3 with square 3. Okay, so in the cohomology of kz mod 2, 3, we're going to see this iota 3 squared, and we're not going to write it as square 3 iota 3 because then that would be overkill, right? We'd see too much stuff if we accounted for both of those. They're the same. Similarly, square 4 square 1 iota 3 is not a thing we'll write down. Again, this has excess 3, so we don't need it. And that's really square 4 on something in degree 4. right? Iota 3 is in degree 3, square 1 takes us up 1. So this is square 1 iota 3 squared, and we start to see this polynomial on squares applied to our fundamental class. Okay, so I want to talk about the proof of this theorem of Serre, that the cohomology looks like polynomial in these square i's on our fundamental class, where I is admissible sequences, or runs over all admissible sequences with xs less than n. We've set up this lemma, so we're ready to go. But in the interest of not making this video too long, let me stop here and we'll pick it up in the next one.